Since the very first spark of consciousness ignited in our ancient ancestors, humanity has been defined by its tools. We are, at our core, tool makers. This innate drive to invent, to innovate, and to improve our condition has been the engine of our civilization's progress. From the sharpest flint spearhead that allowed early humans to hunt more effectively, to the wheel that unlocked new possibilities for travel and trade, each new invention has marked a pivotal step forward. These were not mere objects, they were extensions of our will, our strength, and our intellect. They allowed us to accomplish feats that our biological limitations would have otherwise made impossible. We built tools to overcome the challenges of our environment, making life easier, safer, and more productive for our communities. This long and storied tradition of creation has shaped every facet of human existence. The invention of the printing press did not just make books, it democratized knowledge and fueled revolutions in thought and governance. The steam engine did more than power locomotives and factories. It shrank the world, connected disparate cultures, and fundamentally altered the economic landscape of entire nations. Each technological leap, from the simple lever to the complex circuits of the first computers, has been a new chapter in the epic story of human ingenuity. We have consistently sought to build things that make our lives better, that push the boundaries of what is possible, and that solve the pressing problems of our time. This is our legacy. Now, as we stand in the early decades of the 21st century, we find ourselves on the cusp of the most profound technological shift in our history. The tools we are building today are unlike any that have come before. They are not simply passive instruments waiting for our command. They are dynamic, intelligent, and increasingly autonomous. We are moving beyond creating simple machines that augment our physical abilities. We are now crafting a new generation of tools that can think, learn, and act on their own. This new era is not just another incremental step in our technological journey. It represents a fundamental break from the past, heralding a future that is both exhilarating and deeply uncertain. The dawn of this new age is powered by robotics. This field, once the domain of science fiction and specialized industrial applications, is now rapidly entering the mainstream of our lives. These are not the clunky, single-purpose machines of yesterday. Today's robots are powered by breakthroughs in artificial intelligence, quantum computing, and a vast network of interconnected data. They are becoming more capable, more adaptable, and more integrated into the fabric of our society with each passing day. This evolution forces us to confront a series of critical questions about the path we are on. We have always built tools to serve us, but what happens when the tools themselves begin to surpass our own capabilities? The robotic revolution is no longer a distant theoretical concept. It is happening all around us, right now. It is unfolding in the clean rooms of high-tech manufacturing plants, where robotic arms assemble intricate electronics with a precision no human hand could match. It is present in the vast warehouses of global commerce, where autonomous systems sort and ship millions of packages with tireless efficiency. And it is beginning to appear in our homes and communities, with early model humanoid robots assisting the elderly with their daily tasks or delivering goods in our cities. This new generation of tools is rapidly changing everything we thought we knew about work, productivity, and the very structure of our economy. The change is quiet but relentless, a silent transformation of the world we inhabit. This transition is fueled by a powerful convergence of technologies. At its heart is artificial intelligence, the digital brain that gives robots the ability to perceive, reason, and learn from their environment. AI allows a robot to do more than just follow a pre-programmed set of instructions. It enables the machine to adapt to new situations, solve unforeseen problems, and improve its performance over time. This cognitive power is amplified by the advent of quantum computing, a paradigm-shifting approach to calculation that promises to solve problems of immense complexity, far beyond the reach of even the most powerful supercomputers today. These advancements are not isolated, they feed into one another, creating a cycle of exponential growth in robotic capabilities. The promise of this new era is a world of unprecedented prosperity and well-being. Proponents envision a future where robotic automation has eliminated dangerous and monotonous jobs, freeing humanity to pursue more creative, intellectual, and social endeavors. In this utopian vision, robots will build our homes, grow our food, and care for our sick, leading to a world of abundance where basic needs are met for everyone. They promise to drive our vehicles more safely than we can, manage our planetary resources with greater efficiency, and even help us explore the far reaches of the solar system. The dream is one of a golden age where technology has finally liberated us from the drudgery and limitations that have defined human existence for millennia. However, this gleaming vision of the future is shadowed by profound and unsettling questions. What will this new world cost us? As robots become more capable, they will inevitably begin to take on tasks that were once the exclusive domain of human beings. This is not just about manual labor in factories, it extends to white-collar professions in law, finance, and even the creative arts. If machines can do almost everything that humans can do, but cheaper, faster, and more reliably, what role is left for us? The very real possibility of mass unemployment and deepening economic inequality looms large over the robotic revolution. We are being forced to consider a future where the economic value of human labor diminishes, perhaps to the point of irrelevance. The central question that we must now confront is a stark one. Will this technological leap lead to a better world for all, or will it ultimately render humans themselves obsolete? This is not hyperbole or a fanciful scenario from a science fiction novel. It is the core dilemma presented by the rapid advancement of robotics and artificial intelligence. The potential for good is immense and undeniable. Imagine a world where medical robots perform complex surgeries with flawless precision, extending and saving lives on a massive scale. Think of a planet where autonomous agricultural systems produce abundant food with minimal environmental impact, effectively ending global hunger and restoring our ecosystems. These are the incredible promises that lie just over the horizon. Yet, for every dazzling promise, there is a corresponding peril that demands our careful consideration. The same technology that could create a world of abundance could also create a world of unprecedented social and economic division. If the wealth generated by robotic labor is concentrated in the hands of a small elite, the owners of the machines, the vast majority of humanity could be left behind, disconnected from the economy and stripped of their purpose. This could lead to social unrest on a scale we have never witnessed before, fracturing societies and challenging the very foundations of our political systems. The transition to a robotic age is not just a technological challenge. It is a profound social and ethical one that will require us to rethink our oldest assumptions about work, value, and community. Furthermore, the very nature of the tools we are building forces us to look beyond immediate economic concerns and toward more existential questions. We are steadily marching toward what some futurists call the singularity, a hypothetical point in the future when artificial intelligence will not just match, but dramatically surpass human intelligence. At that moment, our relationship with our creations would be fundamentally and irrevocably altered. We would no longer be the most intelligent species on the planet. The tools we built to serve us could evolve into something else entirely, our intellectual equals, our partners, or perhaps our successors. The implications of such an event are almost impossible to fully comprehend. This journey into the future of robotics is therefore a journey into the future of humanity itself. It touches upon our deepest hopes for a better world and our most profound fears about our own obsolescence. The path forward is not predetermined. The outcome will depend entirely on the choices we make today. It will depend on our wisdom, our foresight, and our ability to steer this powerful technology in a direction that benefits all of humanity, not just a select few. We are the architects of this future, and the responsibility to build it wisely rests squarely on our shoulders. The stakes could not be higher, as we are not just designing new machines. We are designing the next stage of our own evolution. The questions raised by the rise of robotics are too important to be left solely to the engineers, the scientists, and the corporate executives who are building this new world. These are questions that affect every single one of us, and they deserve a global conversation. What kind of future do we want to create? How can we ensure that the immense benefits of automation are shared broadly and equitably? What new social structures, economic models, and ethical frameworks will we need to navigate this unprecedented transition? Answering these questions requires a collective effort, an open and honest dialogue that includes voices from every corner of society, from all cultures, and from all walks of life. This documentary is an invitation to join that essential exploration. We will journey to the forefront of robotic innovation, speaking with the leading minds who are shaping this technology. We will investigate the profound impacts that are already being felt across various sectors of our economy, from manufacturing and logistics to healthcare and agriculture. Our goal is to move beyond the sensational headlines and the simplistic narratives of either utopia or dystopia. We aim to provide a sober, balanced, and deeply researched look at the complex realities of the robotic age, presenting the evidence and allowing you, the viewer, to draw your own informed conclusions about the path ahead. Throughout this exploration, we will trace the development of robotics from its humble origins in the factories of the mid-20th century to the sophisticated, intelligent machines that are emerging today. We will examine the critical distinctions between industrial robots designed for specific tasks and the rise of humanoid robots designed to live and work alongside us. We will analyze the powerful economic forces at play, weighing the incredible gains in productivity against the very real threat of widespread job displacement. This is not just a story about technology, it is a story about economics, politics, and the future of our social contract. It is a story about all of us. Join us as we explore the future impacts of robotics on humanity. We will delve into the incredible technologies that are making it all possible, from artificial intelligence and quantum computing to the awe-inspiring concept of the singularity. We will consider the profound ethical dilemmas, such as the potential for human-machine integration and what it might mean to be human in an age where the lines between biology and technology are blurring. This is more than just a documentary, it's a critical examination of the most important transition our species has ever faced. The future is arriving faster than we think, and we must be prepared to meet it. The concept of creating artificial life, of building machines in our own image, is not a modern obsession. It's actually a dream as old as civilization itself. Ancient myths from around the world are filled with tales of mechanical servants, golden statues brought to life, and automatons crafted by divine artisans. These stories, from the golem of Jewish folklore to the walking tripods of the Greek god Hephaestus, reveal a deep-seated human fascination with replicating the spark of life through ingenuity and craft. For centuries, though, these ideas remained firmly in the realm of mythology and fantastical speculation. The technology to turn these dreams into even a rudimentary reality simply did not exist, and the mechanical men remained characters in stories told around the fire. The first tangible steps toward this automated future came much later, during the Enlightenment and the early industrial age. Visionary inventors and clockmakers began to construct intricate automatons, marvels of mechanical engineering that could write a poem, play a musical instrument, or mimic the movements of an animal. While these were essentially sophisticated toys for the wealthy elite, they represented a crucial shift in thinking. They proved that complex, lifelike actions could be programmed and executed through a series of gears, cams, and levers. This was really the philosophical and technical groundwork for everything that was to follow. The idea of automation was no longer just a myth. It was a mechanical possibility, a puzzle waiting to be solved on a grander scale. The true genesis of modern robotics, however, required a different kind of revolution, one of power and industry. The Industrial Revolution of the 18th and 19th centuries transformed human society, but it was still driven by human hands. Factories were filled with people performing repetitive, often dangerous tasks for hours on end. The dream of replacing this grueling human labor with tireless machines began to take shape as a practical economic imperative, not just an inventor's fantasy. The focus shifted from creating entertaining automatons to designing functional machines that could perform specific useful work. The goal was no longer to mimic life, but to augment labor, to increase output, and to build the foundations of a new industrial world. It was in the 20th century that all the necessary components finally came together. The development of electronics, control theory, and early computing provided the brains to go with the mechanical brawn. The term robot, introduced to the world through a 1920 Czech play, captured the public imagination and encapsulated this new ambition. It would take several more decades of research and development, often spurred by the demands of wartime production and post-war economic booms, before the first true industrial robot would be installed. This marked the quiet, unceremonious beginning of a new era. The long journey from ancient myth to mechanical reality was complete, and the stage was set for the rise of robotics. The modern robot was not born in a gleaming science fiction laboratory, but on the noisy, gritty, and pragmatic floor of the factory. Its purpose was not to ponder the nature of its existence, but to perform a single repetitive task with superhuman speed and precision. The first successful industrial robot, the Humanoid, was installed at a General Motors plant in New Jersey in 1961. Its job was brutally simple: to lift hot, heavy pieces of die-cast metal from an assembly line and stack them. It was dangerous, monotonous work that human workers were happy to give up. The Humanoid never tired, never complained, and never made a mistake. It was the perfect employee for a specific kind of job, and its arrival heralded a fundamental transformation in manufacturing. These early robots were humble in their capabilities. They were little more than powerful, programmable arms, blind and unfeeling, following a predetermined sequence of motions with unwavering accuracy. They could not see their environment, adapt to unexpected changes, or perform tasks that required any degree of judgment. Yet their impact was profound. For the first time, a significant portion of the manufacturing process could be fully automated. This allowed for the production of goods at a scale and consistency that was previously unimaginable. Industries like automotive manufacturing, where precision and repetition are paramount, were the first to embrace this new technology, installing armies of robotic arms to weld car bodies, paint chassis, and assemble components. The economic benefits of this initial wave of industrial robotics were immediate and undeniable. By automating key parts of the production line, companies could increase their output dramatically. Robots could work 24 hours a day, 7 days a week, without breaks or fatigue, leading to unprecedented levels of productivity. This efficiency drove down the cost of manufacturing, which in turn made consumer goods like automobiles and electronics more affordable for a wider population. Furthermore, automation led to a significant improvement in product quality. A robot performs a task in exactly the same way every single time, eliminating the human error that can lead to defects and inconsistencies, resulting in more reliable and safer products for everyone. This initial phase also had a significant impact on the human workforce and the nature of factory work itself. By taking over the most dangerous, dirty, and physically demanding jobs, robots improved workplace safety and reduced the incidence of industrial accidents and repetitive strain injuries. This freed up human workers to move into more skilled roles, such as operating, programming, and maintaining the robots. While concerns about job displacement existed even then, the primary effect in these early days was a shift in the type of labor required. The factory floor was changing from a place of brute force to a place of technical supervision, a trend that would only accelerate in the decades to come. As robotic technology matured, moving from simple hydraulic arms to sophisticated computer-controlled systems, its impact rippled out from the automotive sector to encompass virtually all forms of manufacturing. The initial benefits of speed and precision were amplified, leading to a full-scale productivity revolution that has reshaped the global economy. The data is clear and compelling. Nations and industries that have invested heavily in automation have seen their industrial output soar, even as their manufacturing workforces have stabilized or shrunk. By the year 2025, it is projected that millions of industrial robots will be operational in factories around the world, contributing trillions of dollars to the global gross domestic product. This is not just an incremental improvement, it is a tectonic shift in our capacity to produce goods. This revolution is about more than just making things faster. It's about making things smarter. Modern robotics enables entirely new manufacturing paradigms, such as lean manufacturing and just-in-time production. Robots allow for flexible assembly lines that can be quickly reprogrammed to produce different product variations, reducing the need for massive inventories and allowing companies to respond rapidly to changing consumer demands. This agility creates leaner, more resilient supply chains. The ability to produce goods locally and on demand, rather than shipping them from massive centralized factories overseas, can reduce transportation costs, shorten delivery times, and make the entire global trade network more robust and less vulnerable to disruption. The economic benefits extend far beyond the factory gates. The increased efficiency and lower production costs delivered by automation have a powerful deflationary effect, helping to keep consumer prices low for a vast array of products, from smartphones to household appliances. This effectively increases the purchasing power of people around the world, raising the standard of living. Furthermore, the robotics industry itself has become a major economic driver, creating high-skilled jobs in engineering, software development, data science, and advanced maintenance. The development and deployment of robotic systems has spurred innovation in countless related fields, from sensor technology and machine vision to artificial intelligence and materials science, creating a virtuous cycle of technological and economic growth. We can visualize this transformation by looking at global maps of robot adoption rates. Countries like South Korea, Singapore, Germany, and Japan, which have the highest density of industrial robots per worker, are also global leaders in high-value manufacturing and technological innovation. These charts show a direct correlation between investment in automation and increased industrial output. The message is unmistakable. In the 21st century economy, robotics is not a luxury, but a critical component of national competitiveness. The ability to leverage automation effectively is becoming a key determinant of economic success, separating the nations that will lead the next industrial revolution from those that will be left behind. For decades, the story of robotics was confined to the structured, predictable environment of the factory. The outside world, with its chaos, its unpredictability, and its infinite variables, was simply too complex for the rigid machines of the past. However, powered by exponential advances in computing power, sensor technology, and artificial intelligence, robots are now breaking free from their assembly line cages and venturing out into the wider world. This migration is opening up entirely new frontiers for automation, applying the benefits of robotic labor to sectors that were once thought to be immune to this technological wave. The rise of robotics is no longer just an industrial story, it is a societal one. One of the most promising of these new frontiers is in logistics and fulfillment. The global e-commerce boom has created an insatiable demand for the rapid sorting and delivery of goods. In massive warehouses the size of small cities, autonomous mobile robots now glide silently across the floor, retrieving products and bringing them to human workers, drastically reducing the time it takes to process an order. Outside the warehouse, the revolution continues. Companies are actively developing and testing autonomous trucks and delivery drones that promise to create a fully automated supply chain, from the moment an item is plucked from a shelf to the moment it arrives at a customer's doorstep, with unparalleled speed and efficiency. Agriculture, one of humanity's oldest industries, is also undergoing a profound robotic transformation. The challenges of feeding a growing global population while minimizing environmental damage are immense. Robotics offers a powerful set of solutions. Autonomous tractors can plow fields and plant seeds with centimeter-level accuracy, guided by GPS. Smart drones fly over crops using multispectral cameras to monitor plant health, identify pests, and detect water stress, allowing for the precise application of fertilizers or pesticides only where they are needed. At harvest time, robotic systems are being developed that can gently pick delicate fruits like strawberries or apples, a task that has long required the careful touch of a human hand. Even the construction industry, traditionally one of the least automated sectors of the economy, is beginning to embrace robotics. Large-scale three-dimensional printers can now construct the frame of a house in a matter of days, extruding layers of concrete or other materials according to a digital blueprint. Robotic bricklayers promise to build walls with a speed and consistency that far surpasses human capabilities. On large infrastructure projects, autonomous bulldozers and excavators can perform earth-moving and grading tasks with greater safety and precision. These technologies not only accelerate construction timelines but also improve worker safety by automating some of the most physically dangerous jobs on a building site. While the economic case for robotics is well established, an equally compelling, though less discussed, benefit is emerging: the potential for robots to become powerful allies in our efforts to protect the natural environment. The same attributes that make robots so effective in industry, precision, efficiency, and tirelessness, can be harnessed to tackle some of our most pressing ecological challenges. From reducing waste in our production processes to actively cleaning up the pollution of past generations, robotics offers a suite of tools to help us build a more sustainable future. This environmental dividend may ultimately prove to be one of the most important legacies of the robotic age. This begins right back in the factory. Automated manufacturing processes are inherently less wasteful than their human-driven counterparts. Robots apply paint, sealants, and other materials with exact precision, minimizing overspray and the use of excess resources. Their optimized movements and efficient operation consume less energy per unit produced. By enabling leaner supply chains and on-demand production, robotics reduces the vast energy expenditure associated with transporting and warehousing massive inventories of goods around the globe. These efficiencies, when scaled across the entire global manufacturing sector, add up to a significant reduction in the overall industrial footprint on the planet. Robots are also being deployed on the front lines of environmental cleanup and management. In our sprawling recycling centers, a critical bottleneck has always been the sorting of mixed waste. It is a dirty, dangerous, and difficult job for humans. Now, AI-powered robotic systems equipped with sophisticated machine vision can identify and sort different types of plastics, metals, and papers with incredible speed and an accuracy rate approaching 100%. This dramatically improves the quality of recycled materials, making the entire recycling process more economically viable and effective. In our oceans, autonomous underwater vehicles are being developed to detect and collect plastic waste, mapping pollution hotspots and cleaning up fragile marine ecosystems. In the realm of precision agriculture, the environmental benefits are even more direct. Traditional farming methods often involve the broadcast application of water, fertilizers, and pesticides across entire fields, leading to significant chemical runoff that pollutes rivers and groundwater. Robotic systems enable a far more targeted approach. By monitoring individual plants, agricultural robots and drones can deliver a precise microdose of water or nutrients directly to the root system where it is needed, and apply a tiny drop of pesticide only to the specific leaf where a pest is detected. This approach not only maximizes crop yields but also drastically reduces the use of harmful chemicals, preserving soil health and protecting biodiversity. As the robotic revolution accelerates, it is important to understand that not all robots are created equal. The world of robotics is splitting into two distinct, yet increasingly interconnected domains. On one side, we have the industrial robot, the established workhorse of modern manufacturing. These are the machines that have powered the productivity boom for the past half-century. They are masters of their environment, but that environment is a highly controlled and predictable one, the factory floor. They are designed for a world of repetitive tasks, structured layouts, and precisely defined objectives. Their form follows their function, resulting in powerful arms, specialized grippers, and immobile platforms bolted to the concrete floor. On the other side of this divide, a new and far more ambitious frontier is emerging: humanoid robotics. These are the machines designed not for the factory, but for our world. They are built to navigate the chaotic, unpredictable, and endlessly varied environments that humans have created for themselves. Our homes, hospitals, offices, and cities. To do this, they are often given a form that mirrors our own. A humanoid shape with 2 arms, 2 legs, a torso, and a head is not a matter of science fiction vanity. It is a pragmatic design choice because our world is built to human scale. A robot that can walk upstairs, open a door, and use tools designed for human hands has a massive advantage in navigating our spaces. This fundamental difference in design philosophy reflects a difference in purpose. Industrial robots are tools of mass production designed to optimize efficiency and minimize cost in a commercial setting. They are specialists, each one engineered to perform a narrow set of tasks with unparalleled speed and precision. Their value is measured in output, uptime, and return on investment. Humanoid robots, in contrast, are being developed as generalists. Their purpose is not to produce widgets, but to provide services, assistance, and companionship directly to people. Their value will be measured in their ability to improve quality of life, support human well-being, and integrate seamlessly into the fabric of our daily routines. The distinction between these two types of robots is crucial because it defines the scope and nature of their future impact on society. The story of industrial robotics is primarily an economic one, centered on industries, supply chains, and labor markets. The story of humanoid robotics is a much more personal and social one. It touches upon our most intimate spaces and relationships. How we care for our elderly parents, how we support people with disabilities, and how we manage our daily lives. As these two worlds of automation evolve, one perfecting the art of production and the other learning the art of interaction, they will collectively reshape our entire civilization in profound ways. The industrial robot is a marvel of engineering, a testament to the power of single-minded focus. These machines are the undisputed champions of the structured environment. A modern factory assembly line is their kingdom, a world they have been designed to dominate. Every element within this space is controlled and predictable. The lighting is constant, the floor is perfectly flat, and the components they handle arrive in the exact same position and orientation time after time. In this world, there are no surprises. This predictability is the key to their incredible efficiency. They do not need to think or adapt. They simply need to execute their pre-programmed sequence of motions with flawless repetition. Their design is a direct reflection of this specialized purpose. An industrial robot rarely looks like a person. Instead, it looks like a piece of hyper-efficient machinery. Most are powerful articulated arms, anchored to a fixed point capable of moving with a speed and strength that far exceeds any human limb. They are equipped with specialized end effectors, grippers, welders, paint sprayers, or drills, each one perfectly suited to a specific task. They are single-minded and tireless. They can perform millions of cycles without a drop in performance, a quality that is essential for mass production. Their entire being is optimized for productivity within their cage, making them the perfect engine for the modern industrial economy. However, the very strengths that make industrial robots so dominant in the factory also represent their greatest limitations. Take one of these powerful machines out of its structured cage and place it in the chaotic environment of a city street or a family home, and it would be utterly lost. It lacks the senses and the intelligence to navigate an unpredictable world. An unexpected obstacle, a change in lighting, or an object that is slightly out of place would be enough to cause it to halt or malfunction. These robots are not built for improvisation. Their power comes from repetition, not from adaptation, which confines their direct utility to the highly controlled spaces that have been built specifically for them. This is why, for all their economic impact, most people have never encountered an industrial robot in their daily lives. They remain largely hidden from public view, operating behind the walls of factories and warehouses. They build our cars, assemble our electronics, and package our food, but they do so out of sight. Their influence on our lives is immense but indirect, felt through the price and quality of the goods we buy. They have fundamentally transformed the world of making things, but they have not yet crossed the threshold into the world of human living. For that, a completely different kind of robot is required. The great challenge and promise of humanoid robotics is to create a machine that can leave the factory cage and operate successfully in the complex, messy, and unpredictable world of human beings. This is a monumental undertaking. A humanoid robot must be able to do more than just repeat a task. It must be able to perceive its surroundings, understand context, and make intelligent decisions in real time. It needs to see and recognize objects, navigate cluttered spaces without bumping into things, and interact safely and intuitively with the people around it. This requires a fusion of advanced mechanical engineering with sophisticated artificial intelligence, machine vision, and speech recognition. The humanoid form, with its 2 legs for mobility, 2 arms for manipulation, and head full of sensors, is a strategic choice for this task. Our world, from the height of countertops to the design of doorknobs and the spacing of stairs, has been built by and for bipedal creatures with 2 hands. A robot that shares this basic body plan has an inherent advantage. It can use the same tools we use, move through the same spaces we move through, and perform a wide range of tasks without requiring us to redesign our entire environment to accommodate it. This makes the path to integration much smoother, allowing the robot to fit into our lives, rather than forcing our lives to fit around the robot. The potential applications for such a machine are vast and transformative, touching upon some of society's most pressing needs. Many developed nations are facing the challenge of an aging population, with a shrinking workforce available to care for a growing number of elderly citizens. Humanoid robots promise to fill this gap. They could provide daily assistance in the home, helping with mobility, reminding patients to take medication, preparing simple meals, and providing companionship. They could also support people with disabilities, giving them a greater degree of independence and improving their quality of life. In sectors like hospitality and retail, they could fill labor shortages by performing tasks like delivering food, stocking shelves, or providing information to customers. Of course, the technical hurdles remain significant. Creating a robot with the fluid mobility of a human, the delicate dexterity of a human hand, and the common-sense reasoning of a human mind is still a major focus of research and development. Early prototypes can often appear clumsy or slow. However, progress in this field is accelerating rapidly. Every year, new models are unveiled that are more stable, more capable, and more intelligent than the last. As these machines become more sophisticated and affordable, they will begin to move from research labs into our communities, marking the true beginning of an era where humans and robots live and work side by side. While industrial and humanoid robots represent two distinct paths of development, the future likely lies in a convergence of their strengths. The rigid, powerful precision of the industrial robot is beginning to merge with the adaptive intelligence and sensory awareness once reserved for humanoid research. This is giving rise to a new category of machine, the collaborative robot or cobot. These are robots designed not to replace human workers in a cage, but to work safely and effectively alongside them as partners on the factory floor or in the laboratory. They bridge the gap between the two robotic worlds. Cobots are equipped with advanced sensors that allow them to be aware of their human colleagues. They can sense when a person is nearby and will automatically slow down or stop to avoid any risk of collision. This allows them to operate without the need for physical safety cages, enabling a much more fluid and flexible form of human-robot collaboration. A human worker might perform a task that requires dexterity and judgment, such as aligning a delicate component, and then hand it off to the cobot to perform a task that requires strength or perfect repetition, like tightening a series of screws to a precise torque. This partnership combines the best of both worlds, human ingenuity and robotic efficiency. This collaborative approach is expanding the reach of automation into areas that were previously difficult to robotize. Small and medium-sized businesses that could not afford the cost or complexity of traditional industrial automation can now deploy flexible, easy-to-program cobots to boost their productivity. In fields like medical device manufacturing or laboratory science, cobots can handle sterile materials or perform repetitive pipetting tasks, freeing up highly skilled technicians and scientists to focus on more complex value-added work. This human-robot teaming is proving to be more productive than either a human or a robot working alone. Ultimately, the lessons learned from both industrial and humanoid robotics will cross-pollinate and enrich each other. The robust and reliable hardware developed for industrial applications will provide a solid foundation for the next generation of humanoid robots. In turn, the advanced AI, computer vision and sensor technologies being pioneered for humanoids will find their way back into the factory, creating industrial robots that are smarter, more flexible, and more aware of their environment. This symbiotic evolution ensures that the robotic revolution will not be a simple choice between one type of robot or another, but a rich and diverse ecosystem of machines, each tailored to its task, increasingly working together with each other and with us. The economic story of robotics is a narrative of profound duality, a classic tale of two sides to the same coin. On one side, the benefits are undeniable, tangible, and, well, truly transformative. The relentless march of automation brings with it a wave of economic booms that have the potential to elevate the human condition globally. The most direct impact is on productivity. Robots work tirelessly, with a precision and speed that human hands simply cannot match, leading to a massive increase in the output of goods and services. This hyper-efficiency drives down the cost of production, making everything from cars and electronics to food and medicine more affordable and accessible for a greater number of people around the world. This surge in productivity translates directly into greater wealth creation. As companies become more efficient, they become more profitable, fueling investment, innovation, and economic growth. The robotics industry itself emerges as a powerful new engine of prosperity, generating high-skilled, high-paying jobs in fields like engineering, software development, and artificial intelligence research. The wealth generated by this new industrial revolution could, in theory, fund solutions to some of humanity's most persistent problems, from building sustainable infrastructure to advancing medical research. The promise really is a future of unprecedented material abundance, a world where technology has finally conquered scarcity. However, this gleaming picture of progress has a dark and troubling shadow. The same efficiency that creates so much wealth does so by systematically reducing the need for human labor. Every task that is automated, every job that a robot can perform more cheaply and effectively than a person, represents a potential loss of livelihood. This is the other edge of the sword. The economic benefits of robotics are not abstract. They are created by displacing the economic function of human workers. This creates a fundamental tension that lies at the very heart of the transition to an automated AI, a conflict between the creation of wealth and the distribution of opportunity. This is not a new dilemma. Throughout history, technological advancements have always disrupted labor markets, eliminating old jobs while creating new ones. The farmhand was replaced by the tractor but became a factory worker. The factory worker was later displaced by an industrial robot but could retrain as a technician. The crucial question we face today is whether this time is different. Is the pace and scale of the current robotic revolution so profound that it will destroy jobs far faster than our economies can create new ones? This central uncertainty casts a long shadow over the promise of a robotic future, forcing us to confront the difficult social consequences of our own technological creations. For much of the 20th century, automation primarily affected manual labor in the manufacturing sector. The jobs that were lost were often repetitive, physically demanding, and located on the factory floor. While this caused significant disruption for certain communities and industries, the broader economy adapted. Displaced workers often found new roles in the expanding service sector. However, the current wave of automation, powered by artificial intelligence, is fundamentally different. It's no longer just about automating muscle. It is about automating the mind. This brings the spectre of technological unemployment out of the factory and into every corner of our economy. The list of professions once considered safe from automation is shrinking with alarming speed. Logistics and transportation, which employ millions of people worldwide as drivers, are on the verge of being transformed by autonomous vehicles. The retail sector is being reshaped by automated checkout systems, robotic stock clerks, and AI-driven e-commerce platforms. Even highly skilled white-collar professions are now in the crosshairs. AI can now analyze legal documents, read medical scans, prepare financial reports, and write computer code with a proficiency that is beginning to rival and in some cases exceed that of human experts. No industry, it seems, is immune from this wave of change. The projections from economists and technologists paint a stark picture. By the 2030s, some studies predict that robotics and AI could replace a significant portion of the existing workforce across a wide range of job categories. An animation of these projections would show a steep decline in roles like truck drivers, cashiers, administrative assistants, and even paralegals and junior accountants. This is not a distant, futuristic scenario. It is a trend that is already underway. The potential for social upheaval is immense. A society with a large and permanent class of unemployed or underemployed citizens is a society at risk of instability, social fragmentation, and political extremism. This impending shift forces us to ask a difficult question. What is the purpose of a human being in an economy that no longer needs their labor to function? For centuries, our identities, our social status, and our sense of purpose have been deeply intertwined with our work. A future where that work is no longer available to a large segment of the population would require a radical re-evaluation of our social values. The challenge is not just to manage the economic fallout of mass unemployment, but to navigate the profound psychological and social consequences of decoupling human identity from traditional work. The spectre of technological unemployment is not just an economic crisis, it is an existential one. Even if the most dire predictions of mass unemployment do not come to pass, the economic impact of robotics is poised to dramatically exacerbate income and wealth inequality. The fundamental economic logic of automation is to substitute capital for labor. A company invests in a robot, capital, to replace the ongoing cost of a human worker's salary, labor. In this new economic model, the financial rewards flow primarily to the owners of the capital, the shareholders, executives, and investors who own the robots and the AI systems. Meanwhile, the share of economic output going to labor, in the form of wages and salaries, is likely to shrink. This creates a powerful feedback loop that concentrates wealth at the very top. As automation drives productivity and profits higher, the value of the companies that own the technology skyrockets. This enriches the small percentage of the population that holds significant capital assets. At the same time, the vast majority of people who rely on selling their labor to earn a living find themselves in a weaker bargaining position. With a growing pool of automated alternatives available, the value of human labor in many sectors stagnates or declines. The result is a widening gulf between the robot owners and the robot displaced, a new form of economic division for the 21st century. This trend is already visible in the economic data of the last few decades. Even as corporate profits and stock market valuations have reached historic highs, median wages for ordinary workers in many developed countries have remained flat. Automation and globalization have been key drivers of this decoupling of productivity from pay. The robotic revolution threatens to put this trend into overdrive, creating a winner-take-all economy on a scale never seen before. The social fabric of a society is strained when the perception grows that the system is fundamentally unfair, that the fruits of progress are being hoarded by a tiny elite, while everyone else is left behind. This growing inequality is not just a matter of social justice, it is also a matter of economic stability. A healthy market economy relies on a large consumer base with enough purchasing power to buy the goods and services being produced. If an ever larger share of the population lacks the income to participate in the economy, demand could collapse. Who will buy all the products made by the tireless robots if the majority of people have no money? This is the great paradox of the automated economy. In its pursuit of ultimate efficiency, it risks undermining the very consumer demand that it needs to survive, potentially leading to economic stagnation and crisis. The profound economic shifts driven by robotics are not inevitable forces of nature, they are the result of human choices. This means we have the agency to shape a different outcome. If we are to avoid a future of mass unemployment and extreme inequality, we will need to adapt proactively. This will require a fundamental rethinking of our economic models and our social contract, a deliberate effort to design a future where the immense benefits of automation are shared fairly across all of society. This is honestly one of the most critical policy challenges of our time, demanding bold ideas and a willingness to experiment with new solutions. One of the most widely discussed proposals is the concept of a universal basic income, or UBI. The idea is simple: provide every citizen with a regular, unconditional cash payment sufficient to cover basic living expenses. Proponents argue that UBI could provide a vital economic floor in an age of widespread job displacement, ensuring that no one is left destitute. It would give people the security to retrain for new kinds of work, start their own businesses, or engage in valuable but unpaid activities like caregiving or community work. Early experiments and pilot programs are being conducted around the world, though fierce debates continue about its affordability and potential effects on the incentive to work. Another key area of adaptation lies in taxation. For centuries, governments have funded public services primarily by taxing human labor through income and payroll taxes. In a future with fewer human workers, this tax base will inevitably erode. This has led to proposals for new forms of taxation, such as a robot tax or taxes on data and digital services. The idea is to shift the tax burden from labor to capital, ensuring that the vast wealth generated by automation contributes its fair share to funding the schools, healthcare and infrastructure that society depends on. These policy debates are complex, but they are essential for creating a sustainable fiscal model for the 21st century. Ultimately, the transition will require a massive investment in education and lifelong learning. The jobs of the future will require skills that are uniquely human: creativity, critical thinking, complex problem solving, and emotional intelligence. Our education systems, largely designed for the industrial era, must be fundamentally reformed to cultivate these abilities from a young age. Furthermore, we will need robust systems for adult retraining and skills upgrading, allowing workers to adapt and transition throughout their careers. The goal is not to compete with robots at tasks they are better at, but to double down on the skills that make us human, ensuring that we can work alongside our intelligent machines as partners, not as competitors. At the very core of the modern robotic revolution lies a technology so transformative that it acts as the central nervous system for every advanced machine artificial intelligence. AI is, the ghost in the machine, the invisible intelligence that elevates a robot from a mere automaton into a thinking, learning, and adaptive entity. Early industrial robots were essentially dumb machines, capable only of endlessly repeating a programmed sequence of movements. They could not perceive their environment, learn from mistakes, or handle any deviation from their rigid instructions. Artificial intelligence changes this completely. It gives robots a digital brain, allowing them to process information from sensors, make decisions, and interact with the world in a dynamic and intelligent way. This intelligence is not a single monolithic thing. It is powered by a subfield of AI known as machine learning. Instead of being explicitly programmed for every possible contingency, a robot powered by machine learning can be trained on vast amounts of data. For example, a robotic arm can learn how to pick up a variety of objects not by being given exact coordinates for each one, but by being shown thousands of images and videos of different objects, learning to recognize their shapes, sizes, and textures on its own. This process, often using complex algorithms called neural networks that are loosely inspired by the structure of the human brain, allows robots to develop a flexible and intuitive understanding of their tasks, enabling them to generalize from their experience. This ability to learn from experience is what truly separates a modern robot from its predecessors. It means a robot can adapt and improve over time without human intervention. A robot navigating a warehouse can learn the most efficient routes, adjusting its path based on real-time traffic and new obstacles. A surgical robot can analyze thousands of previous operations to refine its technique for greater precision. This capacity for continuous self-improvement is a game changer, creating a powerful feedback loop where robots become more capable and efficient the more they work. They're no longer static tools, but dynamic systems that evolve, making them incredibly powerful assets in any field they are applied to. Therefore, robotics and artificial intelligence are now inextricably linked. One cannot be fully understood without the other. The physical robot provides the body, the actuators, limbs, and sensors to interact with the physical world. The AI provides the mind, the ability to perceive, reason, plan, and learn. It is this powerful synthesis of intelligent software and capable hardware that is driving the exponential growth in robotic capabilities. Every new breakthrough in AI research, from more efficient learning algorithms to more powerful neural network architectures, directly translates into smarter, more autonomous, and more useful robots that can tackle an ever-expanding range of complex tasks. For many years, the capabilities of artificial intelligence were largely analytical. AI was excellent at recognizing patterns, classifying data, and making predictions based on existing information. However, a new and revolutionary branch of AI has recently emerged, fundamentally expanding the scope of what machines can do. This is generative AI. Unlike its predecessors, generative AI does not just analyze the world, it can create new things within it. It can generate novel text, images, sounds, and even complex designs from scratch. This creative spark is now being integrated into robotics, allowing machines to move beyond simple execution and into the realm of problem-solving and innovation. This technology is revolutionizing the fields of engineering and design, allowing robots to become active participants in their own creation and improvement. For example, an engineer can give a generative AI system a set of goals and constraints for a new robotic gripper, such as its required strength, weight, and range of motion. The AI can then generate thousands of potential design variations, many of which may be completely non-intuitive to a human designer, and test them in a virtual simulation to find the most optimal solution. This process, known as generative design, allows robots to essentially design new and better parts for themselves, accelerating the pace of hardware innovation dramatically. The impact of generative AI also extends to the software that controls the robots. Writing the complex code to govern a robot's behavior can be a painstaking and time-consuming process for human programmers. Now, a developer can describe a desired behavior in natural language, and a generative AI model can write the corresponding code automatically. This drastically lowers the barrier to programming robots, making the technology more accessible to people without specialized coding skills. It also allows robots to adapt on the fly, generating new code for themselves to handle novel situations they have never encountered before, pushing the boundaries of their autonomy and flexibility. This creative capability extends robotics into realms that were previously thought to be safe from automation, particularly those requiring creativity and design. A robot equipped with generative AI could be tasked with landscaping a garden, creating a unique and aesthetically pleasing layout based on a set of general preferences. In a factory, it could design a custom jig or tool needed to assemble a new product. By giving robots the ability not just to do, but to create, we are fundamentally changing their role. They are transitioning from being simple tools that follow our instructions to becoming creative partners that can generate new solutions and ideas on their own. For a robot to operate intelligently in the real world, it must be able to perceive its environment. It needs senses. Two of the most crucial of these are sight and hearing, enabled by the technologies of computer vision and speech recognition. These technologies are the eyes and ears of the modern robot, providing the raw data streams that its AI brain uses to understand and interact with the world around it. Without these senses, even the most intelligent robot would be blind and deaf, trapped within its own processing core and unable to connect with the physical reality it is meant to navigate and influence. Computer vision, or sight recognition, gives robots the ability to see. Using cameras and other sensors like LiDAR, a robot captures visual information from its surroundings. This information is then processed by sophisticated AI algorithms, typically deep learning neural networks, which can identify and classify objects within the scene. This allows a robot to distinguish between a person and a piece of furniture, to read text on a sign, or even to interpret the subtle cues of human body language and facial expressions. This visual understanding is essential for navigation, manipulation, and safe interaction. It is what allows a self-driving car to see a pedestrian or a humanoid robot to find a specific object in a cluttered room. Speech recognition, in turn, provides the sense of hearing and the ability to understand human language. This technology has become commonplace in our lives through voice assistants on our smartphones and smart speakers. When integrated into robotics, it enables a far more natural and intuitive method of human-robot interaction. Instead of using a complex computer interface or a joystick, a person can simply talk to the robot, giving it commands in plain language. A factory worker could tell a cobot to pick up the red component, or a person at home could ask their assistive robot to please bring me a glass of water. This breaks down barriers, making robotics accessible to everyone, regardless of their technical ability. Together, these sensory technologies create a much richer and more contextual understanding of the world for the robot. They allow the machine to fuse multiple streams of information. A robot can see a person approaching, hear them ask a question, and formulate a relevant response based on both the visual context and the spoken words. This ability to see, hear, and understand is what makes true human-robot collaboration possible. It is the foundation upon which robots can move from being isolated machines in a cage to becoming helpful partners, assistants, and companions, fully integrated into the fabric of our human society. Today's robots run on classical computers, but quantum computing is set to revolutionize everything. By leveraging superposition and entanglement, quantum computers could solve complex optimization problems like route planning or assembly almost instantly. This leap could also slash AI training times from months to minutes, accelerating robotic intelligence beyond our current imagination. While still in early development, quantum computing promises a paradigm shift, unlocking breakthroughs in robotics we can barely conceive. The technological singularity is the hypothetical moment when AI surpasses human intelligence and begins to improve itself at an uncontrollable rate. This could transform robots from tools into entities with goals and abilities beyond our comprehension, making the future unpredictable. The singularity forces us to question our role as creators and the risks of building machines that could outthink us. As AI advances, we must balance ambition with caution, aware that we may be approaching this event horizon. Robotics is transforming healthcare, making surgeries safer and more precise with surgeon-controlled robotic arms. These systems enable minimally invasive procedures, faster recovery, and better outcomes for patients. Assistive robots support the elderly, providing mobility, reminders, and social connection, addressing caregiver shortages. Drones and telepresence robots deliver supplies and expertise to remote areas, democratizing access to quality care. Medical robotics is reshaping healthcare, improving lives everywhere. Construction is being revolutionized by robots. From 3D printers building homes in days to bricklaying machines and rebar tying machines speeding up tough tasks. Autonomous bulldozers and drones ensure precision, safety and quality, reducing errors and material waste. These innovations make construction faster, safer and more sustainable. Robotics is setting a new standard for how we build our world. Precision agriculture uses autonomous tractors, drones and robotic harvesters to boost yields and sustainability. GPS-guided machines plant and fertilize with pinpoint accuracy, while drones monitor crop health for targeted care. Robotic harvesters gently pick produce, solving labor shortages and ensuring peak freshness. Robotics is making farming more efficient and environmentally friendly. Robotics is reshaping global logistics, from warehouse robots speeding up order fulfillment to self-driving trucks and delivery drones. These systems cut costs, reduce emissions, and make next-day delivery possible. Autonomous vehicles and drones handle the last mile, bringing packages directly to your door. The future of logistics is faster, smarter, and greener thanks to robotics. In the vast, hostile, and unforgiving environment of space, robotics is not just a convenience or an efficiency booster, it is absolutely indispensable. For any task that is too dangerous, too distant, or too long for a human astronaut, robots are our essential proxies. They are our eyes, our hands, and our pioneers on worlds beyond our own. From exploring the surface of Mars to building the infrastructure for future human settlement, robotics is the foundational technology that makes our dreams of becoming an interplanetary species possible. Without robots, humanity's future in space would be severely limited. The most iconic examples of space robotics are the rovers that have explored the surface of the Moon and Mars. These semi-autonomous mobile laboratories are packed with scientific instruments, allowing them to analyze soil, study geology, and search for signs of past or present life. They can endure extreme temperatures and radiation levels that would be lethal to a human, and they can operate for years on end, dutifully carrying out commands sent from mission controllers millions of miles away. Future generations of rovers will be even more autonomous, capable of making their own scientific decisions about where to go and what to investigate, vastly accelerating the pace of planetary discovery. As humanity looks to establish a permanent presence beyond Earth, robots will be the advanced construction crew. Before the first humans arrive to live on the Moon or Mars, robotic systems will be sent ahead to do the preparatory work. They will 3D print habitats using local regolith, deploy solar arrays to provide power, and excavate underground shelters to protect future inhabitants from radiation. These robotic builders will lay the essential foundation, creating a safe and functional outpost for the human pioneers who will follow. This approach minimizes the risk to human life and makes long-term space colonization a much more feasible proposition. Looking further into the future, robotics will be key to unlocking the resources of the solar system. The asteroids are rich in valuable minerals and water, resources that could be used to fuel a space-based economy. Sending human miners into deep space is fraught with danger and immense cost. Instead, fleets of autonomous robotic mining craft could be dispatched to identify promising asteroids, extract their resources, and process them in space. This would provide the raw materials needed to build and sustain space habitats without having to launch everything from the bottom of Earth's deep gravity well, laying the groundwork for humanity's true expansion into the cosmos. As we peer deeper into the future, the questions raised by robotics move beyond the economic and social to the existential. The technology we are creating is no longer just an external tool that we use. It is beginning to knock on the door of our own biology. The most profound impact of robotics may not be on our world, but on ourselves. As machines become smarter, more capable, and more deeply integrated into every aspect of our lives, we are forced to confront a startling possibility. The clean line that has always separated the human from the machine is beginning to blur, promising a future where Homo sapiens may no longer be the sole or even the dominant form of intelligent life on Earth. This convergence is not a sudden leap, but a gradual process that is already underway. We see its early stages in the sophisticated prosthetic limbs that can be controlled by a user's thoughts, responding with a dexterity that rivals a biological hand. We see it in cochlear implants that restore hearing, directly interfacing with the human nervous system. These are the first tentative steps toward a future where technology is not just worn, but is woven into the very fabric of our bodies. The question is no longer if we will merge with our technology, but to what extent, how quickly, and with what consequences for our identity as a species. This blurring boundary challenges our most fundamental definitions of what it means to be human. Is our humanity defined by our biological flesh and blood, or by our consciousness, our thoughts, and our memories? If a person's mind can be augmented with a direct connection to a computer, are they still fully human? If a significant portion of their body is replaced with superior mechanical parts, where does the person end and the machine begin? These are no longer just philosophical thought experiments. They are becoming practical, ethical dilemmas that we will have to navigate as a society. The future of robotics is forcing us to write a new definition of ourselves. The ultimate trajectory of this trend points toward a future where the distinction between man and machine could disappear entirely. Some futurists envision a world where biological humans and advanced artificial intelligences coexist, perhaps as partners, perhaps as competitors. Others see a future where the two lineages merge into a single new form of life, a hybrid being that combines the evolutionary strengths of biological consciousness with the processing power and physical resilience of a machine. This is the profound crossroads at which we stand. As our robotic creations become more like us, we may in turn choose to become more like them. One potential pathway into this merged future is through cybernetics, the direct integration of technology into our biological bodies and minds. This is not about replacing humanity, but about upgrading it. The goal is to use technology to transcend our natural limitations, to enhance our physical and cognitive abilities, and to evolve beyond the constraints imposed by our biology. This cybernetic path offers a transitional phase, a way for humans to keep pace with the rapidly accelerating capabilities of the artificial intelligences we are creating. It is really a strategy for relevance in an age of intelligent machines, a way of ensuring that we are not left behind by our own creations. The most powerful of these integrations is the brain-computer interface, or BCI. This technology aims to create a direct communication link between the human brain and a computer. Early versions of BCIs are already allowing people with paralysis to control robotic arms or type on a screen using only their thoughts. As this technology matures, it could offer a bandwidth of communication between our minds and the digital world that is millions of times faster than typing or speaking. Imagine being able to access the entirety of human knowledge with a single thought, or to communicate complex ideas to another person telepathically through a shared digital link. This cognitive enhancement could be matched by physical augmentation. Robotic prosthetics will likely evolve to a point where they are not just replacements, but superior enhancements. A cybernetic arm could be far stronger and more resilient than a biological one. Artificial eyes could see in infrared or ultraviolet light, and mechanical legs could allow us to run faster and for longer than any natural athlete. Such enhancements could initially be used to restore function to those with injuries or disabilities, but the temptation to offer them to the healthy as a form of human enhancement would be immense, creating a new divide between the enhanced and the naturals. This cybernetic future raises profound ethical and social questions. Who gets access to these enhancements? If they are available only to the wealthy, will this create a new biological caste system, a literal class of superhumans? What would it mean for society if some individuals possess vastly superior intelligence or physical abilities? The decision to embark on the cybernetic path is a decision to fundamentally alter the human species. It's a future where we take direct and deliberate control of our own evolution, steering it in a direction of our own choosing. The power to do so will be immense, but so too will the responsibility to wield it wisely. Beyond the path of cybernetic enhancement lies a final, even more radical possibility for the future of humanity. Some thinkers and futurists envision a final step in our technological journey, the complete abandonment of the biological human body itself. This concept, often called mind uploading, proposes that it may one day be possible to scan the entire structure of a human brain and replicate it perfectly in a digital simulation. All of your knowledge, your memories, your personality, and the very essence of your consciousness could be transferred from the fragile, wet computer of your brain to a vastly more durable and powerful digital substrate. In this vision, human existence would no longer be tied to flesh and blood. Your consciousness would reside in vast server farms, in the universal digital cloud. You could experience reality through any robotic body you chose, or you could live entirely within simulated worlds of your own creation, free from the constraints of physical law. Death as we know it would become a thing of the past. Your digital self could be backed up, copied, and restored. Disease, aging, and physical injury would become irrelevant memories of a bygone biological era. It is a vision of digital immortality, a new form of existence beyond the limitations that have defined us for our entire history. This concept represents the ultimate expression of the robotic revolution, where the line between human and machine is not just blurred, but completely erased. In such a future, the human species as we currently know it, the biological organism Homo sapiens, would become obsolete. It would be replaced by its digital descendants, beings of pure information capable of thought, travel, and experience at the speed of light. Humanity would have transformed itself into the very technology it created, achieving a kind of cosmic transcendence by becoming a new form of intelligent life, unbound by a single body or a single planet. Of course, this remains a highly speculative and distant vision, and one that is fraught with immense philosophical problems. Is a digital copy of your mind truly you, or just a perfect imitation? What would give a digital life meaning and purpose? Could such an existence become a sterile, meaningless heaven, or a digital hell from which there is no escape? Yet the very fact that we can conceive of such a future is a testament to the speed and power of our technological progress. It is the ultimate question posed by the rise of robotics. Will our creations serve us, merge with us, or provide the vessel for our final, unimaginable transformation? We stand at a monumental crossroad in the history of our species, a pivotal moment that will define the future of humanity for millennia to come. The rise of robotics, powered by the exponential growth of artificial intelligence, presents us with a future of almost unimaginable promise. We have seen how this technology offers a world of unprecedented prosperity, where automation can conquer scarcity and provide abundance for all. It holds the key to building a more sustainable civilization, healing our planet and managing our resources with a wisdom we have yet to achieve. It promises to revolutionize medicine, extend our lifespans, and finally carry us beyond the cradle of Earth to become a truly interplanetary species. This is the gleaming, utopian vision that drives us forward, yet this path to a brighter future is shadowed by profound and existential risks. The same technologies that promise to create immense wealth also threaten to displace millions from the workforce, creating a crisis of purpose and deepening the chasm of inequality. The very intelligence we are instilling in our machines challenges our own position as the dominant cognitive force on this planet, forcing us to grapple with the possibility of our own obsolescence. The journey forward is not guaranteed to be a smooth ascent. It is a precarious path along a knife's edge, with the potential for utopia on one side and the potential for dystopia, a world where humanity becomes a relic of its own creation on the other. The outcome of this grand technological experiment is not predetermined. It will not be decided by the robots themselves, but by the choices we make today. The future is not something that simply happens to us, it is something we must actively build. The responsibility rests squarely on our shoulders to steer this powerful revolution with foresight, wisdom, and a strong ethical compass. We must engage in a global conversation about the kind of future we want to create, establishing new social contracts, new economic models, and new regulations that ensure the benefits of this technology are shared by all of humanity, not just a privileged few. Our success will be measured not by the cleverness of our machines, but by the compassion of our choices. This journey requires us to look beyond the short-term profits and the immediate efficiencies. It demands that we consider the long-term consequences of our actions on our society, our economy, and our very identity. Will we harness the power of robotics to solve our greatest challenges and elevate the human condition? Or will we, in our relentless pursuit of progress, inadvertently create a world in which we no longer have a meaningful role to play? The tools are in our hands, more powerful than any we have ever wielded before. The final choice and the future that results from it is ours, and ours alone to make. We are the architects of what comes next. Ultimately, the robotic revolution forces us to turn our gaze inward and ask the most fundamental question of all. What does it truly mean to be human? For millennia, we have defined ourselves by our limitations and our struggles against them. We were the tool makers, the problem solvers, the laborers. Our intelligence was our unique advantage, our creativity our most precious gift. But what happens when our machines become better tool makers, more efficient laborers, and perhaps even more creative artists and thinkers than we are? When the very qualities we believed were uniquely human can be replicated and surpassed by our own creations, we are left in a profound state of existential re-evaluation. This challenge is not a threat to be feared, but an opportunity to be embraced. It pushes us to discover a deeper, more enduring definition of our humanity. If our value is not in our labor, perhaps it is in our capacity for empathy, compassion, and love. If our purpose is not to solve analytical problems, perhaps it is to create beauty, to build communities, and to explore the depths of our own consciousness. The rise of intelligent machines does not have to diminish us. It can liberate us. It can free us from the drudgery that has occupied so much of our history and allow us to focus on the things that make life truly worth living. Our relationships, our passions, and our quest for meaning. The future will likely be one of deep and intimate partnership between humans and the intelligent machines we create. We will work alongside them, our uniquely human skills of intuition and emotional intelligence complementing their vast processing power and analytical precision. We may even merge with them, using technology to enhance our bodies and minds, taking direct control of our own evolution. The clear, sharp line between human and machine will continue to fade, giving way to a more complex and integrated reality. Our descendants may not be purely biological beings, but they will still be our descendants, carrying the legacy of human consciousness forward into a new and unimaginable era. The story of robotics is, in the end, the next chapter in the story of humanity. It is a testament to our relentless curiosity, our unyielding ambition, and our eternal desire to reach beyond our grasp. The path ahead is uncertain, filled with both incredible promise and formidable challenges. As we step into this new dawn, we are not just building machines, we are crafting the future of life itself. The ultimate question is not whether we can master these new technologies, but whether we can master ourselves, guiding our creations and our own evolution with the wisdom and humanity they demand. The journey has just begun.